Hi girls, today we are going to see about toroid in the third chapter. So what is a toroid? A toroid is nothing but a solenoid bent in such a way that its ends are joined together to form a closed ring shape is called a toroid, which is shown in figure. So this is the toroid diagram. So if you bend the solenoid so that the ends meet together, then it is called a toroid. So it is a circular form of a solenoid. You can say it as the circular form of the solenoid. And here when you see the magnetic field inside the toroid, it is uniform, that is constant magnitude. Whereas when you see the exterior and interior region, the magnetic field is 0. And for this you see this diagram, and in this diagram you take 3 points P, which is interior to the toroid, and Q, which is outside toroid, and S is that is inside the toroid. So when you see at the interior of the toroid, the magnetic field, you can see that it will become 0, and outside the toroid it is also 0, but somewhere inside the toroid it has some constant value, that is at the point S. That derivation we are going to see now. And first when you see the open space interior to the toroid, so here we have to construct a ampere loop of radius r1. And so here taking r1 as radius, you draw an ampere loop, and this ampere loop is nothing but an imaginary loop. And in this loop, when you see L1 is equal to, for simplicity, you can take L1 is equal to 2 pi R1, that is the circumference of this circle. And what is Ampere circuital law? Integration over the loop 1 Bp vector dot dl vector is equal to mu naught I enclosed. Here this loop encloses no current, because inside the toroid there is no current, so the current becomes 0. So the right hand side of this equation becomes 0. This is possible only when the magnetic field in the point P vanishes. So Bp vector becomes 0. That means the magnetic induction at the point P is 0. And the next topic, open space exterior to the toroid. For that you consider this point Q. Again you consider the Amperian loop whose radius is R3. So in such a case you can take L3 is equal to 2 pi R3. And here what about integration for loop 3 BQ vector dot DL vector is equal to mu naught I enclosed. Here when you see the current coming out of the plane of the paper is cancelled by the current going into the plane of the paper. So one direction the current is going inside, and in other way it is coming out. Both of them get cancelled, so I enclosed becomes 0. So the right hand side of this equation becomes 0. This is possible only if the magnetic field at the point Q vanishes. That means BQ vector is equal to 0, which means that is outside the toroid, the magnetic field is 0. Next when you see inside the toroid, that is, for that you consider the point S, and here the radius you take it as R2. And what about here L2? L2 is equal to 2 pi R2. So the equation as usual, you take the Ampere circuital law equation, and here integration for the loop 2 Bs vector dot dl vector is equal to mu naught I enclosed. Here when you take n be the number of turns of the toroid, then I enclosed is equal to ni. Therefore the equation becomes integration for loop 2 Bs vector dot dl vector is equal to, since this is a dot product, we expand this and write it as cos theta, and here B vector and dl vector are acting in the same direction, so theta will become 0. So you will get Bs, and integral dl becomes 2 pi R2. But already you know this equation, integration over a closed surface Bs vector dot dl vector is equal to mu naught ni. This is for the solenoid equation. And so when you equate equation 1 and 2, you will get Bs is equal to mu naught ni by 2 pi R2. So here what about n? N is number of turns per unit length. So the equation becomes Bs is equal to mu naught ni. So we can say that outside the toroid and we have seen the three cases. Open space interior to the toroid, the magnetic induction becomes 0, and when you see for the point exterior to the toroid also the magnetic induction becomes 0, whereas for the point inside the toroid the magnetic induction will have the value B is equal to mu naught Ni. Next we are going to see about force between two long parallel current carrying conductors. For that you consider this diagram. Here there are two long conductors A and B, and the currents passing them through them are I1 and I2. They are flowing in the upward direction. That is, the current is flowing in the same direction, and the distance between the two conductors is equal to R. And here when you see B1 is a magnetic induction at the wire A, and when you see here the unit vectors I cap, j cap and k cap, you can find out the directions from this unit vectors. And so here let I1 and I2 be the electric currents passing through the conductors A and B in the same direction, that is they are passing along the Z direction. And so here already you know this equation B1 vector. B1 vector is the magnetic field at a distance r due to the current I1 in the conductor A. So here B1 vector is equal to mu naught I1 2 pi r into minus I cap. Here we are taking minus I cap because the reason is given, because according to thumb rule the direction of magnetic field is perpendicular to the plane of the paper and inwards. That is, you can show it in the form of cross, that is it is flowing inwards, means that is in negative I vector. So here you are having negative sign. And so next we are going to see about Lorentz force, and you know the Lorentz force equation dF vector is equal to for a small element dl which is at the next conductor B. So first we have seen the current flowing through the conductor A. Now you consider here a small elemental length dl in conductor B, and so here dF vector is equal to I2 dl vector cross B1 vector. Here I2 is a current flowing through the second conductor, because of that you are having another magnetic induction. So I2 dl vector cross B1 vector, and instead of B1 you can substitute mu naught I1 by 2 pi r, which is a current that is magnetic induction to the straight conductor, and here minus because the force is acting directed towards the conductor, so you can take it as minus k cap cross I cap, because the direction of dl is along k cap and the direction of B is minus I cap, so the minus is taken outside, so k cap cross I cap, and you know k cap cross I cap is j cap, and you retain the negative sign. So minus mu naught I1 I2 dl by 2 pi r j cap, and here the elemental length dl in B is attractive towards the conductor A. So here the force is towards the conductor A. That is, when you see this diagram, the force in the conductor B is towards the conductor A. That is towards the left hand side. The force is towards the left hand side. Now what is force per unit length? For that you divide this equation by L. So you will get F by L. After integrating and dividing by L, you will get F vector by L is equal to mu naught I1 I2 2 pi r divided by 2 pi r j cap. Here you are having negative sign, and the negative sign is because the force is acting in the towards the left direction. And here, so next we are going to see for the another conductor B, and so here and for the next conductor B, B2 vector is given by mu naught I2 2 pi r I cap, and so here you are having positive sign here, because according to thumb rule the direction is perpendicular to plane of the paper and outwards. There in the first case it is inwards, but here it is outwards, so the arrow is out of page, so here you can use the dot. And so here what is dF vector in the for the conductor, and dF vector is a magnetic force on the element dl of the conductor A, because of that magnetic induction there is a force on the conductor A. So dF vector is equal to I1 dl vector cross B2 vector, because here I1 is a current flowing through the conductor A and it experiences a force due to the magnetic induction B2. So you are having I1 and B2. And substitute for B2, so you will get mu naught I2 by 2 pi r in the place of B2, and here k cap cross I cap, because k cap is the direction of dl vector and I cap is the direction of B2 vector. And so here there is no negative sign, so you will get the same expression. And here the length dl is attracted towards the conductor B. So here it is acting towards B, that means both the conductors, the force is attracting towards each other. And so here the force, when you see this diagram, you can understand I1 is a current flowing through conductor A and I2 is a current flowing through the conductor B, and B1 is towards the, and you are having B1 and B2. B1 is a magnetic induction due to the current I1 and B2 is a magnetic induction due to the current I2, and according to the thumb rule, you are having F vector and F vector which are towards each other. That is, when the currents they are flowing in the same direction, the force is here attractive. And in the first conductor it is shown by dot, that means the force is acting outwards, and in the next diagram the force is shown in the cross, that means the force is acting inwards. And so here also F by L is equal to mu naught I1 I2 by 2 pi r into j cap. So when the currents carrying conductors is attractive if they carry current in the same direction. So when you see this diagram, you can understand here the two conductors A and B, they attract each other, and so when the current flow in the same direction, this will happen. And so suppose if the current flow in the opposite direction, the force will be repulsive. So you see the force between two parallel conductors is repulsive if they carry current in opposite directions. And this diagram shows that here the currents flowing in the opposite direction, here the magnetic induction is somewhat different, so they will be repulsive in nature. And from this you can define what is 1 ampere, and already have studied this definition in your 11th standard. 1 ampere is defined as a constant current which when passed through each of the two infinitely long parallel straight conductors kept side by side parallel at a distance of 1 meter apart in air or vacuum causes each conductor to experience a force of 2 into 10 power minus 7 Newton per meter length of the conductor. And so this is already studied, that is you are defining ampere from this derivation, and so 2 into 10 power minus 7 Newton is produced. If such a case, when this force is produced, then that constant current is called as 1 ampere, and there are some conditions, and they kept side by side parallel, and they should be kept at a distance of 1 meter apart, and they should be kept in air or vacuum. So in such a case, if a force is 2 into 10 power minus 7 Newton per meter length, then you can say that the current passing through that conductor can be taken as 1 ampere. Next we are going to see about torque on a current loop, and this is very responsible for motor operation. That is, we are using motor everywhere in our mixie, washing machine and grinder, everything there is a motor, fan, and for motor operation this principle is used. Here torque on a current loop placed in a magnetic field. Suppose if current carrying loop is placed in magnetic field, it will experience a rotating force, that we are going to see in this part. When you see this diagram, there are two poles, north pole and south pole, and there is uniform magnetic field existing between the north pole and the south pole, and a coil is placed PQRS, and the length of PQ is A and the breadth of the coil is B, that is in QR, and here the coil is placed perpendicular to the magnetic field, and n vector is a normal vector, normal to the plane of the coil, and theta is the angle between the normal of the coil, normal to plane of the coil, and the magnetic field. And this theta, you should remember, theta is the angle between normal to plane of the loop and B, that is magnetic field, and we shall see the derivation one by one. And here when you see the current carrying arm PQ, that is the current carrying arm PQ is having length A, and so here you know F vector is equal to IL vector cross B vector. So instead of IL you can substitute IAB, and this is a cross product, and the angle between IL vector and B vector in the first case, that is for the arm PQ, is pi by 2. So since sin pi by 2 is equal to 1, FPQ is equal to IAB, and according to Fleming's left hand rule, this is upwards. This is not according to right hand rule, but it is according to Fleming's left hand rule. There is some mistake in this part, and so here the force is acting upwards. So when you see this diagram, the arm PQ will move upwards, and now next you take the arm QR, which is shown in this diagram, and for this QR, the FQR is given by IBB. The small b is the breadth of the coil, and here the angle is pi by 2 minus theta, and because the direction of QR with the magnetic induction becomes pi by 2 minus theta, so that will become IBB cos theta, and so here the magnitude of this is BIB cos theta. And third case, you are considering for the arm RS, and for RS you are having FRS is equal to IAB sin pi by 2 as in the arm PQ, and so here sin by pi by 2 will become 1, so IAB, and this direction is downwards, and so when the arm PQ move upwards, the arm RS will move downwards. This is shown in the diagram. FPQ vector is upwards and FRS vector is downwards, whereas when you see FQR is downwards in this direction and FSP is in the upward direction, both these directions will cancel each other because they are acting on the same line. So FQR and FSP will cancel each other, whereas only these two forces will exist, that is FPQ vector and FRS vector will exist. And so when you see for the third case, for the fourth case, FSP is equal to IBB sin pi by 2 plus theta, because here you are having the angle as pi by 2 minus theta, and for this arm it is pi by 2 plus theta, so will IBB cos theta. And so here, as I have already told you, FQR and FSP are equal, opposite and collinear, because they are act in the same line, so they cancel each other. But whereas FPQ and FS vector, they are equal in magnitude but opposite in direction, and they are not acting along the same straight line, so they constitute a couple which exerts a torque. So only these two forces are responsible for exerting the torque. And when you see this diagram here, this is a part of the diagram, and here when you see the center part is a coil, and here you know this angle is theta, that is angle between the unit vector and the magnetic induction is theta, and here FPQ vector acting upward direction, FRS vector in the downward direction, and if suppose this angle is theta, and in this diagram this angle is also equal to theta, and this diagram this angle will also become equal to theta. So here, since the center part it is, so b by 2, you can take it as b by 2, and so this part when you draw a perpendicular, that is equal to b by 2 sin theta, because sin theta when you say opposite by hypotenuse, so you will get b by 2 sin theta. And so here tau PQ is given by now b by 2 sin theta, because you know tau is equal to distance into force, and so here the distance is b by 2 sin theta into IAB, because already we have calculated the force which is equal to IAB and points the direction of AB. And similarly the torque acting on the arm RS is given by tau RS is equal to b by 2 sin theta IAB, because here the perpendicular distance is b by 2 sin theta. You have already know that is tau is equal to perpendicular distance into one of the forces, and so here from this diagram the perpendicular distance is equal to p by 2 sin theta. And so here the total torque is the addition of 2, so p by 2 sin theta FPQ plus p by 2 sin theta FRS. So when you substitute, that will become b by 2 plus b by 2 will become b sin theta, and FPQ and FRS is equal to IAB. So taking common terms outside, you will get b by 2 sin theta plus b by 2 sin theta will become b sin theta. So tau is equal to IAB sin theta, because area into breadth will give you capital A into B will give you area, which is given by IAB sin theta. And in a vector form you can write tau vector is equal to IA vector cross B vector. It also can be written as tau vector is equal to PM vector cross B vector, because in the previous class we have studied PM vector, that is magnetic dipole moment, is equal to IA vector. So instead of IA vector you can substitute PM vector. So suppose the tendency of the torque is to align the normal vector with the direction of the magnetic field, and suppose if there are n number of turns, tau will become tau is equal to NIAB sin theta. And here there are some special cases. And first case, when theta is equal to 90 degree, that means the plane of the loop is parallel to the magnetic field, because you know the theta is the normal to the plane of the coil. So it will take in the opposite way, that is when theta is equal to 90 degree, the plane of the loop is parallel. So the torque becomes maximum, because tau cos theta, when you see tau is equal to NIB sin theta, the theta will become 90 degree. So tau maximum is equal to IAB. When theta is equal to 0 or 180 degree, then the plane of the coil is perpendicular. In this case, the torque becomes 0, because the angle is 0 or 180 degree, and sin 0 will become 0. So this is about torque on a current carrying loop in a magnetic field. Hope you understand, girls.